Hello and welcome back. Today in this session we are going to work with Gauss's law. So far we took discrete charges and worked. Say for example there is 1 coulomb of charge, 2 coulomb of charge, 4 coulomb of charge, minus 2 coulomb of charge, or maybe microcoulombs. So these are discrete charges. Correct? But say for example, if we have a surface of a charged conductor, then it is a continuous distribution of charge if we see at the macroscopic level. Of course, I understand at the microscopic level, the charge distribution is discontinuous. But at the macroscopic level, we see the continuous charge distribution. In that case, we divide the area into small areas and we call them area element. We consider each area element and work. So, let's start. Let us consider continuous charge distribution. So, say for example, if I have considered the surface of a charged conductor, then it is feasible to consider a small area element, say delta S, on the surface of that charged conductor and specify charge delta Q on it. For example, another surface, I can consider a small area element here. Okay. So, if there is a surface, then I can divide that surface into small area elements, say delta S, and specify a charge delta Q on it. Correct? Hence, we can define charge density. For surface, we'll define surface charge density. Let us give a symbol sigma for that. How do we define it? Surface charge density sigma at the area element delta S is given by delta Q divided by delta S. What it means? Charge delta Q on that area element divided by this area of that element. So, surface charge density sigma is equal to charge per unit area. The units for surface charge density? Coulomb per meter square. Let us consider now linear charge distribution and consider a small length element, say delta L. Let the charge on it be delta Q. If I use a symbol for linear charge density as lambda, then linear charge density will be equal to delta Q by delta L. What are the units for linear charge density? Coulomb per meter. Similarly, if I consider a volume and a small volume element there, then the volume charge density rho equal to delta Q by delta V. What are the units for volume charge density? Coulomb per meter cube. Right? Now, if I want to find what is delta Q here, it is delta Q is equal to rho multiplied by delta V. So, if we want to find electric field at a point due to this continuous charge distribution, then it is obtained by summing over the electric field due to such small volume elements. So, what do we get? Electric field will be almost equal to 1 upon 4 pi epsilon 0 summation of rho into delta V. This is the charge on that small volume element divided by r square into unit vector r for over all this delta V. So, we are summing up over all such volume elements. As delta V tends to 0, this summation sign will change to integral sign. Okay. Let us understand Gauss's law. We have already understood the concept of flux. So let us consider this spherical surface. Let a charge Q be enclosed in that, say plus Q charge. Let R be the radius of this sphere. Let me consider now a small area element here. So that area element subtends a solid angle at the center. Let this be the radius, correct? If this is radius, this also is radius towards that small area element. So what will be the radial direction here? This is the radial direction. So if I had considered this small element here, the radial direction would have been in this direction. If it is here, this is the radial direction, correct? So if this is the area element, then what is its direction? We call it area vector, right? It is in the radial direction. So this is delta S. The electric field at that point also will be perpendicular to the surface. Therefore, it will be in the same radial direction. Correct? So, the flux through an area element delta S will be given by, we already know it, it is, say delta phi will be equal to dot product of these two vectors, that is E and delta S. So delta phi is equal to vector E dot vector delta S. What is the value of electric field at that point? It is given by E is equal to 1 upon 4 pi epsilon 0 Q upon R square into unit vector R. Let us substitute this electric field value in this equation. So what I get? Delta phi is equal to 1 upon 4 pi epsilon 0 Q upon R square, and it will be dot product of unit vector R and vector delta S, area vector. Now we already know that this unit vector has magnitude 1 and R and delta S are in the same direction. So the angle between them is 0. So what will be the magnitude of this? It will be R into delta S into cos theta. Now we know theta is 0. So cos of theta, that is cos of 0, is 1. Hence, what will be the answer for this? R unit vector R dot delta S will be equal to delta S, right? So delta phi will be equal to 1 upon 4 pi epsilon 0 Q upon R square into delta S, since delta S and R have the same direction. All right. Now total flux. If we have considered a small area and found the flux delta phi, so if we want to find the flux through the whole spherical surface, then it will be equal to sum of Q upon 4 pi epsilon 0 R square into delta S, right? For all such delta S. Now this is constant, so I can take it out of the summation sign, and that will be equal to Q upon 4 pi epsilon 0 R square into summation of delta S. Now what is the total surface area of the sphere? 4 pi R square, right? So hence total flux coming out of that spherical surface will be equal to Q upon epsilon 0, right? So Gauss's law states that electric flux through a closed surface, say S, enclosing charge Q, is given by Q upon epsilon 0, where epsilon 0 is permittivity of free space. So let us see now some points to remember. These are very important points. Gauss's law is true for any closed surface of any shape. So we have considered here spherical surface. So it's not necessary that it is true in case of only spherical sphere. It can be of any shape. All right. So that is very important. It has to be closed surface. Second point, the charge Q is the total charge inside that enclosed surface. The charge may be located anywhere inside. It's not necessary that it has to be at the center of this closed surface, right? Next, the right hand side, what I mean by right hand side is this right hand side of this equation. So what is it? Q upon epsilon 0. So this Q, the total charge, is the charge enclosed inside the surface. Any charge outside the enclosed surface does not contribute for this flux. Okay. The surface which we choose here is called Gaussian surface. And this Gaussian surface cannot pass through discrete charges. We have to take care that it should not pass through discrete charges, but it can pass through continuous charge distribution. It is easier to calculate electric field when there is symmetry. So hence, we should choose a suitable Gaussian surface. Now that we have understood the Gauss's law, we will see some applications of Gauss's law in the next session. That's all in this session. See you next time.